All right, this is going to be Chem 1211, section 3.1 to 3.3. So we're starting in chapter 3. This is atomic structure, but now we're going to be talking about the properties of elements with how they behave, and we need to talk about electrons for that. We already talked about protons and neutrons and stuff, so we're going to dive into electrons here. Before we can start talking about electrons, though, we have to talk about light, because light and electrons have a lot of things that are similar. So a photon is a packet of light, and light moves as a wave and also as a particle, and electrons actually do the same thing. So light is kind of easier for us to understand, and then we can get electrons. And when we're talking about how we know the structure of an atom, a lot of it has to do with experiments that were done with light. And so we're going to start with light. Energy can be absorbed by particles, and then they can give off energy and re-emit energy. So you absorb some, and then it's like inhaling and exhaling. Like you absorb some, you give off some. Sometimes the giving off some looks like visible light spectrum, and so we see things like light, like things that give off light. Different elements emit different colors of light. That's actually how we know how old stars are, in that they give off different colors of light, and we can, with fancy spectroscopes and things like that, figure out what element the star has in it when we get that light. And if it's a young star, it'll have more hydrogen, for example. If it's an older star, it'll have some heavier elements. And so we can kind of chart what's going on with that. The light from the star to the point that we get it, right? And the star may already be dead by the time we get that light, but at least we kind of can tell what was there. So we're talking about light, we're talking about the electromagnetic spectrum. So when like a chemist or a physicist talks about light, we're talking about all of this, everything from radio waves, which are the lowest energy light, all the way to gamma, which is the highest energy. Now, when you talk about light with your friends, or if you talk about light to a family member or something, you're probably talking about only visible light, which is this tiny little amount of all of the light that the sun gives off that we can actually see. We have two things. We have wavelength and we have frequency. So with wavelength, it is the distance. I think I have a slide specifically. Yeah, so wavelength, we'll come back to that previous slide, but wavelength is the distance between two crests of the wave or two troughs of the wave. And the wavelength is given by this symbol lambda. So this is the wavelength of wave A, is from here to here, and the wavelength of wave B would be from here to here. Now, wavelength corresponds to the frequency, which would be this symbol nu. So wavelength is this symbol lambda, and the symbol kind of looks like a wave, right? It's like a cresting wave. You think about surfing on that wave there. And then we have this other symbol nu, which is the frequency. And the frequency is basically how often does the wave, if you were to put an anchor down, so let's say we were to put like a boat and an anchor down, how often would I be bobbing up and down on that wave? That's the frequency. And it's usually how many times we pass a certain point with the wave per second. Wavelengths are usually in this equation particularly, they're in meters, and frequency is in inverse seconds. Or you can write it as inverse seconds or hertz. You may have seen hertz if you're like looking at your radio or your microwave, right? It's giving you energy it's giving you the energy which is related to the frequency in hertz. And especially if you know anything about radio, like you're on a certain frequency, and that's how the radio waves are picked up and sent out. I usually do the math with it as 1/seconds because that's easiest for me to see how my units cancel. Hertz is like disguised as 1/seconds, and then the S to the -1 usually just confuses people because we don't remember that that's actually the same thing as 1/s. C is the speed of light, and we're going to use 2.998 times 10 to the 8 meters per second, and that's why the wavelength is in meters. A lot of times the wavelength of what we actually are looking at are in nanometers or smaller. For like visible light, for example, is in nanometers, but we use meters for this formula because the speed of light is represented in meters here. So this formula, C is equal to the wavelength times the frequency. We can also rearrange it to say frequency is equal to C over lambda. So as we can see, if wavelength increases, because this is constant, frequency would decrease. So this is an inverse relationship. I want you to think about if you're on a boat on wave A and you're anchored, you would bob up and down less frequently than if you were on a boat on wave B and you're anchored, you'd be bobbing up and down a lot more. So short wavelength, higher frequency. Long wavelength, lower frequency. Going back to the electromagnetic spectrum real quick, we have our longest wavelength is radio waves. And so we'll think about radio waves as long waves. So I'll draw a wave here. So we'll think about radio waves as long waves. That's a little ugly. So radio waves is longer waves. We'll do like that. And then I want you to think about gamma rays as really short wavelengths. And it's much bigger difference than what I'm drawing, but let's just go with me there. Now, we talked about the relationship between wavelength and frequency, but I also want to talk to you about the relationship between wavelength and energy. So imagine that I'm on a boat on a radio wave. There's my little boat. It's got a little flag. Here I am on my boat. And draw myself big enough to give myself any sort of face. I'm on my little boat. Maybe I have a hat because it's sunny outside. I'm on my boat on this wave. I'm having a nice time, right? This is a long wavelength and a low frequency. That's new. And it's a low energy. We're cruising on this wave. It's nice. It's relaxing. Hopefully you don't get seasick, but it's relaxing, right? Now imagine that I'm on a boat and this is what the waves look like. Oh no, we're having a real hard time. My boat is broken in half. Okay. I'm flying through the air. I'm no longer having a fun time. My hat's over here. All right. Uh, this is no good. So this is a short wavelength, a high frequency, and high energy. So frequency and energy are directly related, and wavelength and frequency are indirect, and wavelength and energy are also indirect. So think about those two waves as we go. So gamma rays are the highest energy, lowest wavelength or smallest wavelength, highest frequency. Then radio is the opposite, and visible light's right in the middle. Visible light is higher energy than microwaves. Visible light is higher energy radiation than microwaves. I think that we have it in our heads that just because a radiation is a certain type of radiation, that it's dangerous. Yes, ultraviolet X-rays, gamma rays, we don't want those. Those cause problems. That's why we wear sunblock. And our atmosphere filters out most of all that nonsense. But if you're in space without an atmosphere, you have to wear a special suit because you just get irradiated with gamma rays. And that would not be fun. But the visible light we use to see is much higher energy than infrared, which is actually heat energy, and microwaves. I'm not saying you should get into your microwave and turn it on or anything like that, but I mean, you can increase the amplitude of a wave and increase its power, right? So that's a little bit different. But the frequency of the actual wavelength, and the energy of one photon of that type of energy is maybe not as high. It's like if you just have one photon of any one of these, one bundle of light for any one of these, I'd rather get hit with a radio wave than with a gamma ray photon. But if you tell me, okay, you're going to get in the microwave and the microwave is going to have, 10 million photons hitting you versus just one gamma ray hitting you, it's different, right? So don't always take it as like, oh, it's all microwave. I can get into a microwave and microwave myself and it'll be fine because it's less energy than visible light. But a one photon of a microwave is less energy than a visible light. With visible, we go Roy G. Biv in order of increasing energy. So red, orange, yellow, green. We used to call it indigo, or sorry, blue, and then indigo and violet, but we got rid of indigo, said it actually is just blue and violet. So Roy, ROYG, Biv, blue and violet. Red is the lowest energy wavelength, looks more like this, and violet is the highest energy, looks more like this. The reason our stop signs are red is because um, now everything, all of this goes at the speed of light in space. But as soon as you hit the atmosphere, as you know, like light in water diffracts and it changes, right? Light also in our atmosphere changes. So when we have an atmosphere and a medium like an air that it goes through, these waves actually travel faster than these waves. So we see red faster than we would see other colors. That's why stop signs are red, is because we will see them faster. Also why if you have a red car, I think you have higher insurance because if you're speeding, the cops will see you more often. I think that's what I was told when I was young and driving for the first time. So we're gonna use this formula. So make sure that you're just familiar with like, hey, if I plug something in here, how do I rearrange this formula algebraically? Um, Sunlight is not continuous. There are these lines at which we don't have light. You don't need to really worry about knowing what they are. It's just an interesting thing your textbook decided to tell you. Basically, how we figure out, we'll talk about this in the next video, but basically how we figured out the structure of where electrons are in the atom is based on atomic spectrum and based on the fact that a chemist named Niels Bohr looked at light given off of hydrogen in a tube and he sent electricity through it. So you heat it up or gave energy to the hydrogen in the tube and then looked at what it gave off using a prism essentially and found that this light given off by the hydrogen separates into these specific bands of visible light. And so that caused him to think, well, I think maybe the electrons moving around in hydrogen are moving in specific discrete ways because we see these specific bands of visible light being given off. We'll talk more about that in the next video. This is called an emission spectrum when we look at only what is given off, and an absorption spectrum is just the opposite. It looks at only what is being absorbed by the detector. I don't think you have to worry about this too much in lecture, and I don't think that you have anything in lab where it goes into too much detail on this. You might have a little bit of something, but don't worry too much about it. Black body radiation. Black body radiators are perfect absorbers of light when they're cold and perfect radiators of light when they're heat. So when they're hot. I don't think that you need to know anything related to black body radiation or this graph or anything for your exams in this class. What I do want you to know, though, is this relationship between energy and wavelength and frequency. So I'm going to fill this in because for some reason it's not. This is called Planck's constant, H, and it finishes out this formula. And this formula relates the energy. Now, specifically, this E is the energy of a photon. A photon is a packet of light energy. Um, this H is Planck's constant, and the nu is the frequency. Now, if we combine this equation with this equation, combine this one and this one, so combine this E equals H nu and C equals lambda nu, we get this equation. So you can relate wavelength to energy using this equation. You will have to memorize these. So I recommend that you memorize these two and then just know how to algebraically connect them. I'm not drawing nu correctly here. So if you're good at algebra, you don't have to memorize the big connector one. If you want to memorize that one, you can. But I recommend that you memorize these two and then understand that you can solve one of them for frequency and then plug that into the other one for frequency because they have a common variable. So we're going to do an example problem. What is the energy of a photon with a wavelength of 349? So if I give you the formulas one more time and have you pause the video, try to solve this. Let me give you the constants as well. The constants are actually on your periodic table equation sheet, but you have to memorize the formulas. But the constants are given to you, but I'll write them here. So wait to pause for just a second until I write them out. All right, go ahead and pause and give it a try. All right, I hope that you paused it and gave it a try. So we want to know the energy of a photon, and the wavelength is 349 nanometers. And I'm trying to relate energy and wavelength. Well, they don't belong in the same formula, so I have to solve for frequency in one of the formulas and then plug it in. So this one already says energy equals. I'm going to leave this one alone. So what we're going to do is we're going to solve for frequency here and then plug it in where it says frequency here to get our relationship. So how do I solve for frequency? Divide both sides by lambda. So I get frequency is equal to C over lambda. So nu is equal to C over lambda. We're going to take that C over lambda. We're going to plug it right in here. So we get E is equal to H C over lambda. And we can rewrite it as E equals HC over lambda or CH over lambda, however we want to think about it. Now we can plug in, right? Wrong. You have to check your units. Look at the units for C, meters per second. Nanometers is the wavelength I'm given. So we have to turn this into meters. So nano is equal to 10 to the negative 9. That's what's on your flashcards. We can add meter to both sides and then put a 1 in front. So we can take our 349 nanometers and we can say 1 nanometer is equal to 10 to the negative 9 meters, and that will give us 3.49 times 10 to the negative 7 regular meters. We cancel out our nanometers over there. So there's the dimensional analysis. And again, what I mentioned in class this week, or I hope I mentioned in class, is that dimensional analysis should be a quick and easy tool to grab. So you have to do enough practice with it to where it becomes a tool you're comfortable with because we're going to use it a lot in general chemistry. All right. So we have now we have this is going to be where we plug in for wavelength. So now we have our wavelength and we have our two constants. So let's look at this. We're going to say E is equal to H. And notice when I write out my algebra, I'm going to write out my units because the units help me double check and triple check my work. If the units don't work out to what I want, then I didn't do it correctly. And then I'll plug in my meters, not my nanometers, because I can't cancel meters with nanometers. So meters will cancel, seconds will cancel, and I'm left with joules, which is the unit for energy that we're using. I don't think I mentioned that. Let me go put this back up here. Is that energy of the photon, and the unit is joules. J equals joules. So if we do all of this, and I made this problem up, so I don't have it memorized. Let me plug it in real quick. Make sure that you're very familiar with how to use the correct scientific notation in your calculator, because we're going to be doing a lot of that as well, especially in this unit with this content. Make sure you know how to plug it in correctly, because if you plug in that bottom number incorrectly, you get the wrong answer. So you should be getting we want three significant figures, 5.69 times 10 to the negative 19 joules. If you don't get that, it's probably because you didn't put parentheses around this number before you divided it, or you're not using the EE button for your exponent. So if you don't want to put parentheses around this, you have to use EE as your exponent before you divide it. You can't type in like times 10. Because if you do divided by 3.49 and then you say times 10 to the 7, it'll put the 10 to the 7 on the top. Because remember, everything that your calculator sees as multiplied thinks it's on the top of the fraction. This is what you should be getting. If you have struggles with it, send me a picture of your calculator. I'll help you figure out how to type it in. Last, oh, I thought we were almost done. So yeah. Give me 1 second. Sorry, I think I accidentally deleted something I wasn't supposed to in here. 1 moment, please. Please hold. So yeah, we're actually done with this video. Because I actually just deleted a slide didn't need to in here. So we're done with this video. Thanks for hanging out. We'll see you later.